Hi, hope you had a good evening, good day, and you're able to watch this. This is a precursor to our trigonometry section. A couple of things that you have to be comfortable with in order to be successful with trig. So let's get started. Today we're going to review how to use the Pythagorean theorem. So whenever you hear right triangle, this should always come to your mind. We're going to use it to find missing measures of sides of triangles. Then we're going to, as a result of finding those measures, we're going to have to remember how to rationalize a radical in the denominator. And then finally, in order to help us keep things straight and orderly for trig, we have to correctly label sides of a triangle. Right, so let's get started with the Pythagorean theorem. Here we go. The Pythagorean theorem is a squared plus b squared equals c squared. The thing to remember is that a and b have to be the legs. The legs are the two sides that join to make the right angle. So that has to be A, that has to be B. Now when I say has to be, this could be B, this leg could be B, and this leg could be A, all right? The one that has to be defined is the one across from the 90-degree angle, and that's C. The hypotenuse must always be across from that right angle, okay? It doesn't matter if I call this side B or A, or this side B or A, but this side is a must. Must. Okay, that's a must. Wow, can you read that? This is a must. Okay, so let's give it a whirl, see what we get. All right, use the Pythagorean theorem to find missing measures. When we start, it helps if you label the legs A and B. Label the hypotenuse, which is always across from the right angle, C, and it is right there. Okay. Write your formula down and plug into a squared plus b squared equals c squared. You know how I am. The more you write something, the more it becomes a memory. So write your formula each time. I do it still, and I'm a mathematician, and I still write my formula. So it's not a sign of weakness, it's a sign of understanding. So a squared is 3 squared, so that's 9. Remember, you're not multiplying by 2. You are multiplying by the same number, so you're squaring. Okay. B is 4, so I get plus 16 is equal to c squared. Don't know it, that's what I'm looking for. Okay. Now I add these two together and I get 25 is equal to c squared. I'm not interested in c squared. I had to get c squared in order to finally get to C. So I have to take the square root of both sides. Remember, square rooting undoes squaring. So over here, I'm left with just C, and then this is 5. Okay, so 5 is equal to C. Often we're not looking for the hypotenuse. Often we know the hypotenuse and we have to therefore figure out one of the legs. The good news is that you get to use the same formula. The thing you want to be careful of is making sure you plug into the formula correctly. So again, label your legs A. The legs meet at the 90-degree angle. They meet here, all right? So A is equal to 5. B, we're looking for, we don't know it, and C, our hypotenuse, because it is across from the right angle, is 13. I write my formula, and I plug into the appropriate places. 5 squared, again, is not 2 times 5, it's 5 times 5, so that's 25, plus B squared is equal to 13 squared, is 13 times 13, which is 169. It may help you to have a list of perfect squares. You might want to make that. I've made it for you in the past. Now would be a good time for you to make it for yourself. Now, in order to solve for B, I have to subtract 25 from both sides. and I get b squared is equal to 144. I recognize that to be a perfect square, which is 12 times 12. So when I take the square root of both sides, this is like doing 12 times 12, and I have a perfect underneath there. So b just equals 12, just like that. Why don't you try this one on your own? Hit the pause button and come back and see if you got it right. You will get a large number under the radical sign. All right, welcome back. Label it A, B, and C. A is already labeled for us. If that was an X, we would mark it as an A for our A spot. This is B, and this is C. Again, I get to use the same formula, even though I'm not looking for C itself. Goes back to that saying when two things are equal, you set them equal to each other. So A, I don't know. I get A squared plus B is 6, so 6 squared is 36. And 15 squared is a 225. Now I subtract 36 from both sides, and I get A squared is equal to 189. Now I have to take the square root of both sides because square rooting undoes squaring. And now I would have to simplify this 189, which takes us into the next concept, simplifying radicals and rationalizing them from the denominator. When you simplify radicals, you want to look for any perfect squares, or you want to use prime factoring and pull out all the doubles of prime numbers. Anything you pull out front gets multiplied together. Any factor you leave under the radical gets multiplied together and stays under the radical. If you have a situation where you have a radical, let me go to my highlighter, a radical in the denominator, then what you're going to do is you're going to be sneaky, and you are going to multiply top and bottom by that radical. Why? So that we end up with a perfect square in the bottom, and we can remove the radical. We want to get the radical gone in the denominator. Our first example is a square root of 48. That doesn't have a radical in the denominator. So we ask ourselves, is it perfect? Well, it's not, because 49 is a perfect square. That would be 7 times 7. So we know we're going to have to use some prime factoring. So I look at 48 and I say, oh, it's even. I know it's divisible by 2. Okay, but it's also, if I look at 4 plus 8, that gives me 12. Those digits add to a number that is a multiple of 3. So 48 is also divisible by 3. So 3 and 16. And then I recognize 16 is a perfect square. It's 4 and 4. Once I hit a perfect like this, I can stop, and I can pull out that double and as a single, and then leave my 3 under the radical. So that's 4 square roots of 3. Remember, anytime you have a double under the radical, that's like x squared, it comes out in front of the radical as a single. Now we have to simplify the square root of 3 over 2. All right? So I have that pesky little radical in the denominator, and I can't simplify it at all. I can't remove it. So what I do is I force it to be a perfect square by multiplying it by itself. Whatever I do to the bottom, I must do to the top. Okay? It's a little mathematical gymnastics. All right? Now look here. I have the square root of 2 times the square root of 2. That's like having a pair of 2's under a radical, right? So that just simplifies to a single 2 in the denominator, just like that. Any pair under the radical comes out as a single, all right? You might want to write that down. Any pair under is a single in front. Sorry. I know that looks crummy. Sorry about that. Okay. And then now I just multiply 3 times the square root of 2. And we're done. So here we go. Let's try this one more time. I got to this slide once before and all my numbers were a mess. So I had to stop it and start it all over again. All right. Number 1, the square root of 54. All right. 54 is not a perfect square. From 49, the next one is 64. I'm sorry. Yeah, 64. Yeah. All right. So what I have to do here is I have to start looking. My thing is going crazy. Make sure I'm on my pen. I have to start prime factoring. And I'm going to divide by 3 because 5 plus 4 equals 9. So I'm going to divide by 3 and I get 18. And then I'm going to divide by 3 again and I get 6. And then this is just 3 times 2, which I'm going to end up having to multiply together again anyway. All right? But look, I have a pair of 3's here. They come out front as a single. And then my other 2 I multiply together underneath the radical. Problem number 2, I have the square root of 5 and look where it's sitting. It's sitting underneath it's in the denominator. So I'm going to be tricky and I'm going to multiply top and bottom by the square root of 5. And I do that so that I force this denominator to have a pair of 5's underneath the radical. Any pair simplifies to a single, so my denominator is just 5. And then I'm left with 3 square roots of 5. And when I say 3 square roots of 5, I'm implying 3 times the square root of 5. All right, now I have the square root of 12 over 3. Okay, so I'm going to look at the square root of 12 first, and I'm going to divide by 3, and I get 4, and divide by 2, and I get 2, and there's my perfect there. So I get 2 square roots of 3 over 3. Now you have to ask yourself, am I done? I have a radical, but look where it is. It's in the numerator, so it's fine. I don't have a radical in the denominator, so I get to stop right there. That one was cake. Okay. Number 4, we're going to try the same thing. I'm going to go offside here and do 32. If I divide by 2, I get 16. Oh, there's that perfect again. And so I get 4 and 4. Okay, there's my perfect pair. I have a pair underneath, so that means I bring it out front. I still have a 2 under the radical, and then I have a 2. Notice here, I'm going to backtrack a little bit because I want to make another point. Look back here at 3. Notice I didn't try and cancel the 3 with the square root of 3. Those aren't the same thing because this one is under the square root symbol. So it doesn't cancel. It doesn't have the same value as 3. It's a number multiplied by itself to get 3. All right? And then notice over here, now move back over here to 4 with me, okay? I cannot cancel the 2 into the square root of 2 because this doesn't have a radical, or this has a radical, this doesn't. But I can cancel the 2 into the 4. And I'm just left with 2 square roots of 2. This square root of 2 in the denominator, you're going to see a lot in trig, so we want to get used to seeing what to do with that. We're going to multiply top and bottom by the square root of 2, and we get the square root of 2 over 2. Remember, this is nothing more than 2 times 2 under a radical. every pair comes out as a single without the radical. All right. Third concept, final concept, here we go, making our way through. Correctly labeling a right triangle to be successful in trig. Okay, so every right triangle has one right angle. Okay, in this case, angle C is the right angle. And as I've been saying, the hypotenuse is always across from the right angle. Always, 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 always. Always across from the right angle. Notice that the right triangles have two other acute angles, two additional angles. Angle A, let's focus on angle A, all right? Angle A also has a side that's across or opposite. We call it opposite. Notice that I've highlighted that O. I've made it really big. Okay, so this is the side opposite because it's across. And angle A also has a side adjacent. All right, and so I've labeled that side with a big A. Each of these angles has a side opposite and a side adjacent. And it's important that we know how to label them and recognize them. Okay. Angle B, I've made that one bigger. Now we're focusing on angle B. All right. It also has a side opposite to it or across from it. Call it opposite. And it has a side that's adjacent to it. Call it A. So we have an O, an A, and an H. Okay. We're going to use O, A, and H for trig ratios and trig functions. So let's get used to seeing those. Right? All right. For the indicated angles, label the side opposite, the side adjacent, and the hypotenuse. Well, this is the angle in question here. All right. So the side opposite is across or opposite, that's our O. The side adjacent is by its side, here's A, and the hypotenuse is always across from the right angle. Again, A, O, H. Now let's do angle B. It has a side opposite, okay, and it is O. All right. Now, make sure that you're picking up this little difference. B has two adjacent sides, but one of them is across from the 90-degree angle, so it is the hypotenuse. The adjacent is the other one, not the hypotenuse. That's the adjacent. Why don't you try and label these last two and see how you do. Hit the pause button, come back and see. All right, welcome back. Here's the angle of concern. It has a side opposite, it has a hypotenuse, and it has a side adjacent. Here is our angle of interest B. It has a side opposite, it has a side or a hypotenuse across from the right angle, and it has an adjacent side here. So hopefully you understand that. We'll be working through some problems tomorrow in class. Thanks so much for listening. We'll see you tomorrow.